This is the second lecture for eigenvalues and eigenvectors. Let us consider a matrix A. The matrix A is 1, minus 1, minus 1, minus 1, 1, minus 1, minus 1, minus 1, 1. This is a 3 by 3 matrix, and you say that this is a symmetric matrix. Okay, so the eigenvalue equation, is Ax is equal to lambda x, or A minus lambda I x is equal to 0. Say this is equation 1. X is eigenvector and lambda is eigen, and the characteristics equation is determinant of A minus lambda I is equal to, okay, A minus lambda I is equal to. So if you substitute values of A and the identity matrix, and you will obtain 1 minus lambda, minus 1 minus 1, minus 1, 1 minus lambda, minus 1, minus 1, minus 1, 1 minus lambda is equal to. Now R1 dash is equal to R1 minus R2. That means subtract the row 2 from row 1, and similarly subtract row 3 from row 2. And we see that by this operation the determinant is 2 minus lambda 0, and this is 0, 2 minus lambda, minus 1, minus 1, 1 minus lambda is equal to 0. And you see that 2 minus lambda is common in the row 1, and 2 minus lambda is also common in row 2, so that we can write 2 minus lambda, 2 minus lambda, and 1 minus 1, 0, 0, 1, minus 1, minus 1, minus 1, 1 minus lambda. And if you simplify this, you will see that 2 minus lambda, 2 minus lambda, and 1 plus lambda is equal to 0. Say this is equation 3. So this is the characteristics equation. Okay, and you see that eigenvalues are lambda 1 is equal to, say this is lambda 1 minus 1, lambda 2 is equal to 2, and lambda 3 is equal to. So the two eigenvalues are equal. This is called twofold degeneracy. This is called twofold degeneracy. So let us find the corresponding eigenvectors. So start for lambda 1 is equal to minus 1. Lambda 1 is equal to minus 1. 1 minus lambda minus 1 minus 1 minus 1 1 minus lambda minus 1 minus 1 minus 1 1 minus lambda. This and the eigenvectors x1, x2, x3 are the components, and for eigenvalue lambda 1, eigenvector is 1, so this is 1 1 1. So x11, x21, x31 are the components of eigenvector 1, and this is lambda 1 lambda 1 lambda 1. Okay, so if we put lambda 1 is equal to minus 1 in this equation, so it reduces to 2 minus 1 minus 1 minus 1 2 minus 1 minus 1 minus 1 and okay, x11, x21, x31 is equal to okay. Hence we have three homogeneous equations. We have three homogeneous equations. The first one is 2 into x11 minus 1 into x21 minus 1 into x31, and so that we have 2 x11 minus x21 minus x31 is equal to 0. Say this equation is 4. Now minus x11 plus 2x21 minus x31 is equal to 0. This is 4b, and minus x11 minus x21 plus 2x31 is equal to 0. 4c. Okay. Take 4b at first. Okay. So from 4b we see that x31 is equal to this. Take minus x31 to the right side, so that x31 is equal to minus x11 plus 2x. So this is equation 5. Okay. Now substitute the expression of x31 in equation 4. So from 4a and equation 5, that we have 2x11 minus x21 minus of x31 is minus x11 plus 2x21 is equal to 0. Is equal to 0. Or you see that, and this will add up x11 minus 3x21 is equal to 0, and we finally obtain that x11 is equal to x21. Okay. Say this is equal to some constant alpha. Say this is constant alpha, some arbitrary constant. This arbitrary constant. Okay. Now substitute the values of x11 and x21 in equation 5. So from 5 you see that x31 is equal to minus of x11 is alpha, x21 is 2 times of alpha is equal to alpha. Okay, so the eigenvector, x1 is equal to x11, x21, x31. These are the components, and we have already found the values of the components. x11 is alpha, x21 is alpha, x31 is alpha. Alpha is arbitrary constant. You can take it 100, minus 100, no matter. But we express the eigenvector in terms of unit vectors. So the norm of vector x1, and it is denoted as x1 is equal to this x11 square, x21 square, x31 square. Sum of the squares of the components. And this is 3 alpha. Okay, root over 3 alpha. So the unit vector is x1 by norm of x1. This is 1 over root 3 alpha and alpha. Okay, and so that finally you see it is 1 over root 3, 1, 1, 1. Okay, so the eigenvector for lambda 1 is equal to this. So for lambda 1 is equal to minus 1, unit eigenvector is 1 over root 3, 1, 1, 1. Okay. Now let us find the eigenvector for second eigenvalue, and second eigenvalue is 2. Okay. Now it is replaced by 2, replaced by 2, replaced by 2, and this is also the last index 2, 2, 2. Okay. So if you substitute this, you will see that 1 minus 2 is minus 1, 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 minus 1. This and x12, x22, x32, okay, is equal to 0, and you see that all the three equations are same. So minus x11 minus x21, sorry, 1, 2, 2, 2 minus x32 is equal to 0. All three equations are equal. So that you can write, say, x12 is equal to minus x22 minus x32. Okay. In this situation, you can choose any of these values. Say x32 is equal to some value. So there is no restriction. You can choose it 0, minus 3, minus 4, anything. But here we choose x32 is equal to 0. x32 is equal to 0. We choose. Okay. And the equation, say this is equation 6. And the equation 6 reduces to x12 is equal to minus x22. Okay, and you can say this is equal to beta, some arbitrary constant. So now the vector x2 is x21, x22, x32. x21, sorry, x1, x1, x12 is beta, x22 is minus beta, x32 is 0. And norm of this x2 is equal to beta square root 2. So the eigenvector, the unit eigenvector x2 hat is equal to x2 root 2 beta minus beta 0, 1 over root 2, 1 minus 1, 0. Okay, 1 minus 1, 0. So for lambda 2 is equal to, so the lambda 2 is equal to 2, and the unit eigenvector x2 hat is equal to 1 over root 2, 1 minus 1 and 0. Now x, now for lambda 3 it is also 2. The eigenvalues are same as lambda 2. So if you substitute all these values, you will arrive in the same equation for the case of lambda 2. So how do you find the third unit vector along the third eigenvector? This is a trick, and the trick is x3 eigenvector is the cross product of these two, x1, x2. Okay, because eigenvectors are orthonormal, unit eigenvectors are orthonormal. Okay, unit eigenvectors are orthonormal. So this cross product will give you the third one, which is orthonormal to both x1 and x2, and this x3 corresponds to the eigenvalue lambda 3. Okay, so we can see this is a vector like I, j, k. Okay, so ordinary cross product. So 1 by root 3 and 1 by root 2 I, j, k, 1, 1, 1, and this is 1 minus 1, 0, and this is 1 minus 1, 0. Okay, and if you take the cross product, you will see this is root 6 this is root 6, and for this you will see minus I minus j is equal to plus j, and for k it is minus and minus 2k, and now write it in this way. So root over 6 1 sorry minus 1 1 and this. Okay, something is wrong, 0, this is plus 1, this is okay. So that lambda 2 x3 is equal to 1 over root 6 1 1 minus 2. And you can check that all the eigenvectors are orthonormal. All the eigenvectors are orthonormal. Okay.